Alright, what's going to happen to you when you get exposed to radiation? Your cells will be programmed for death. Often you'll be exposed to burns. There is a thing called radiation sickness. It has its own symptoms, and eventually death. Longer term would be cancer and birth defects in children, as certain cells are extremely sensitive to radiation and ionizing radiation. In this case here are things like your gamete cells in your sex organs, and the gut lining is really sensitive. I think the internal lining of certain arteries and all that sort of thing really doesn't like radiation. Chernobyl, and I believe that's Supercorn from Chernobyl too. Oh, this dude here, and Yasser Arafat. This is Litvinenko. He was the spy from Russia that defected to the UK, met up with a couple of his old KGB mates, and they put polonium into him. Died a couple of weeks later in an agonising death from alpha radiation. See, normally alpha wouldn't matter. If I had an alpha radiation source and I was putting it here, okay, let's just stick it here on the screen, I wouldn't worry because it wouldn't get anywhere near me, even if it was highly radioactive. But the thing is, when you inject it into someone, or as Litvinenko did, take it in with a cup of tea, it would have been coursing around his veins in the bloodstream, just radiating the crap out of his internal organs and melting him from the inside. So yeah, he died of acute radiation sickness. They reckon that this bloke here used to lead the Palestinians, Yasser Arafat, that some Swiss labs actually detected the products of polonium poisoning on his clothes. This is, I think there's a better way to write this. You run away, so you increase your distance from the source. So the further away you are, the less damage it can do to you. Or you can put something that will protect you from it. So gloves, masks, tongs. You can reduce your exposure time. Long-term exposure is more dangerous. Often people working in medical areas will have to wear special badges that detect how much radiation they've been exposed to. And then there's shielding. So for alpha particles, you need gloves or clothes. Beta particles are normally plastic gloves or a sheet of aluminium. And gamma and X-ray radiation, you need concrete and lead. That's a slide that refers to that whole Chernobyl thing. And as bad as it was, there's some very, very interesting aspects here. Some of these animals, because the rate at which they're exposed to ionizing radiation is higher than that of other animals, they're actually evolving and coping to live in that environment. There's some rare sightings of this, like almost extinct horse that used to live in the wild in Russia is back, Przewalski's horse or whatever it is, and one of the more interesting things I saw was I was some kind of, like, what do they call them? British people put them in their pants. Ferret, that's it. It's like a ferret thing, the stoat, and they looked at the incidence of cancer in these stoats that were around Chernobyl, and they compared them to the same species 300 kilometers away, and the incidence of cancer at Chernobyl was far less because the exposure to greater levels of background radiation, well, it actually switched on a whole bunch of genes that prevented the growth of cancer in these things, and consequently, these animals, yeah, they were way better at dealing with cancer and just suppressing it. Whereas, you know, the normal stoats 300 kilometers away, because they weren't exposed to these high levels of radiation, they didn't have the survival mechanism turned on, so they ended up getting these sort of cancers a lot earlier. And this occurs in the human race too. Now, half-life. Half-life is the time it takes for a nuclear substance to decay by half, and it's represented by lambda, which also means wavelength, but in this case it's half-life. Now, it can be microseconds and millions of years. Short half-lives mean that things are going to radiate real quickly, and a long half-life means that it's going to take a long time to decay. You can plot it on a decay curve, and it's a measure of the probability of decay. So you're not going to know which atom in any particular substance will decay and when, but you can predict how many of them will, and it's quite accurate. So in this case here, we've got an example of the decay of cesium-137. Start out with 100 of whatever kilos, and then after 30 years, which is its half-life, you've got 50 kilos of cesium left. And it's not as if like the cesium has totally disappeared. It's just become a different element through the transmutation process, and it'll keep going down and down and down and down and down until basically there's none left. Like you're not going to have like a 0.1 of a cesium atom, and you'll get to a point where the last cesium atom will eventually just decay. And here's an example question for you. Technetium-99, and this is for real, this is what we use all the time. It's often used for medical diagnosis. It has a half-life of 6 hours. A patient has 30 micrograms injected into their bloodstream. How much is left after 12 and 48 hours? So why don't you have a shot at that? We'll have a look at the answers in a tick.